So yes, Ankit, tell me.
Okay.
I started. Okay. So hello everyone. Thank you for coming. And now I'll continue with what showed very nicely. And he showed things on kind of system level. And I work more on the device level. And this is what I'm going to try to give you two examples that I think maybe we can discuss later and see how we can bring this together to the thing that you do. Just this is the agenda that we're going to have today, and you already saw it. And as after this, we'll continue with the presentation stuff from your side, and after this, we'll finish with some lunch and breaks and so on. So I'll give you two examples. I'll try to be quick. The examples are linked to speeding up numerical simulations. And the other is, I call it biosensors because I have a PhD student working in biosensors and devices, and I want to give you a different flavor of what we do. So by no means, it's not the main thing that we do here, but this is something that we can be complementary to the things that you do. So Richard told you that you have different, I'll claim that this thing is a transistor here in a second. But in a moment, you can think this box, it's a rectangular box, and it has one material which is in the middle of silicon, and it has another material which is the blue one, which is silicon dioxide. And what Richard was telling you that usually when you make the circuit, you want to make it with some technology that has specific width and length, and you don't really want to invent kind of arbitrary numbers here. So we kind of, in the purpose of this, just to show that the machine learning with my work with the device technology and TCAD, we just took arbitrary boxes to train the machine learning model. It doesn't mean that it's physically accurate. It means that we just did the job to play and see what we can do. So the main objective is, if I want to simulate this with physical models, which means numerical equations that you saw on the computer that we do, like so-called TCAD simulations, can we use this somehow link with the machine learning here, which is on this side, in order to speed up the simulations. Why we want to speed up the simulations? Because usually, if you go to companies like some of you work with ST Microelectronics, they pay a lot of money for licenses. And this license, if the job runs 3 days, 5 days, 15 days, 2 hours, whatever, this license is directly linked with the cost per hour, right? So if you speed up the numerical simulations one way or another, you literally can save money. One of the things, and you can make it faster. There are two ways to speed up simulations. What people do, GPUs, right? You throw this on the GPU, more computational power, you get more output. The other method is to be smart mathematically and numerically and kind of solve this in a clever mathematical numerical way. And maybe third method is, can we train machine learning to give initial guess, which is a bit better, in order to speed up the simulation. So this is kind of the third thing that we're trying to do. So these are the questions that we have. So we have, we want to know if this is a nanowire. So what you're going to have here is, you're going to, maybe for the guys to be sure. So if this is the box that you see here, you have a source and a drain. So you have a current that you want to go from left to right, and you want to calculate the current because this is the main output that you want to measure and simulate. And I know that I can calculate this current that goes through this piece of silicon or semiconductor using differential equations. Can I just replace this using machine learning, and how we can make it faster? So I can do this with TCAD. There is something which is called, you can simulate. So for the guys, maybe for the students, maybe there are different flavors of simulations. There are different kind of level of complexity. This is what Richard was telling you. So at some point you need to draw a line and says, okay, I need to accept this approximation, but I want to be sure that I'm not so wrong, right? So when you have a device with nanoscale dimensions like this is something which is called quantum confinement effects. What it means literally is they're in two directions. So quantum effects in these devices that Richard was kind of showing you, that we reach this FinFET technology, play an important role. What it means is that if I have a source and a drain here, and I try to push electrons from left to right, if this is very short, this is going to tunnel through. So the electrons, like a wave, is going to tunnel through the device. which makes not nice output because you cannot turn off the transistor. The switch that you have, turn it on and off, it cannot be turned off. And the other quantum confinement effects are linked to this kind of part of the transistor, which is the cross section. You need to confine the charges. So the way to solve this is something which is called non-equilibrium Green's function formalism. We are not going to go much into details, but this is the quantum way of solving the problem. And the other thing is, all of the simulations, when you do numerical simulations, most of you, Professor when does this as well, it's something which is called self-consistent loop. I don't know if you know, I mean, the students really don't know much, but self-consistent loop means that usually I have two equations, in this case for some, and the other case is current, so equation here. You need to solve them in a loop until you reach some tolerance to finish the job. So, and you start with some kind of wrong case of the system. If you go numerically, and who can do, probably Alex know better than me what it is, but what is this self-consistent loop? What you say here is you can see relatively error versus iterations. So when you solve any equations numerically, usually there are two ways, or two kind of rules that you follow. One is called linear scaling, which is the orange line, and the other here is quadratic scaling. As you can see, the green one kind of scales faster. So if my tolerance is 10, let's say 5 to the minus 4, the green line, we're going to reach this tolerance of around 12 iterations, and this guy probably will reach around 25. So it's going to be twice longer. So if you solve this for, let's say, 3 hours, this is going to be 6 hours or something similar. So unfortunately, most of the equations that we have, like kind of the numerical equations, follow the yellow line, not the green. And especially our negative code kind of follows this yellow line, which again depends on the device. We can argue that it's not great because it oscillates a lot, but nevertheless, even if you make it great, you cannot make it quadratic. You still on the yellow line. So the question is, can we speed up these quantum corrections to make the things faster and to solve this problem significantly quicker? So to give you a feeling, some of the simulations really can run 2 or 3 days. It depends what you want to do. And the way is, can we move from here is initial guess to here, which is the ML input, basically to be able to kind of jump all of this process or all of this oscillation that are going from the beginning to the end. And we did this kind of 2 years ago, I think, and there were only 2 papers back then. So this is some of our colleagues in Korea, and this what we did is just, by the way, this was a student like you guys doing internship with me, that he developed this, and these are some of the people that they're around. And we wanted to see, can we use something black box? Richard said it's not good to use it, but we just decided to see if we can push the boundaries. Can we use a convolutional machine learning method to accelerate this quantum simulation software? So from our point of view in Vihar 5, maybe we can think about it that maybe we also might be able to use some of these black boxes just to make our life faster, easier, and better, even if it's a black box. In this case, we don't worry too much, at least to my way of view, if we understand everything, right? So we just make the things faster. So as I said, we are doing this in kind of to solve numerical equations. You have 2 ways. One is have better mathematics, and better and faster, you mean, in this case, I have a PhD student, he will come in a bit, probably to see you, Leo. He will work with this open source code that we can talk about later, how you can make open source code module to this and maybe make a company, as Richard was explaining to us. This we can talk about this later. Or the other is to use machine learning to do the things quicker and faster. So I'll give you a very quick kind of overview on this. And there are 2 equations that you need to solve. One is called Poisson, the other is called Negev, but let's say this is charge. This gives you charge, and this gives you current. Sorry, this gives you current and charge. This gives you a potential. What you need to do is solve them self-consistently, but what you can do also is to feed them to machine learning in order to have better initial guess and finish with the output, which you can run. What we did in this specific case, just to play, we took 3 devices, which means we took 3 cross-sectional areas with different dimension, different lengths, and different width. We trained on 2, and we wanted to predict on the 3rd one. Why it's important? Because every time when you go and ask someone, you train this machine learning model on this specific system, how transferable is this? Like Richard was telling you. So you need to have, so it's a black box approach. You really don't know what are the limitations. But if you train on 2 or 3 systems that are slightly different but similar in the same way, you hope that you can extrapolate or interpolate for a system that is slightly different. So if I train between 10 and 15 for some parameter, maybe I'll predict 17, hopefully, in a way, or definitely I should be able to predict 12. So this is what we do in a way. And we split what we did also kind of from your view when you do kind of the simulation part, we split in different slices. So we have different kind of vectors or arrays for positional encoding. I'll show in a second, for charge, for potential, for different gate biases and width and height and so on. So I think the main kind of message of this presentation is this table, which we call it location map. And I think is this kind of very similar what Zettelen machine does in a way that Richard was explaining. So what you have here, you have a normal neural network, but you have positional encoding that comes with one of the layers. So what it means this is that, so if I have this guy, this is the transistor that I'm trying to simulate or the system. If I go from left to right, I'm going to be along x-axis, okay? If I go along this side, I'm going to be on the y-axis. The problem is when we started doing this is that when you calculate, when I calculate charge and potential here, I'll go further. When I calculate here potential on this side and this side, in the middle, you have maybe 5 or 6 orders of magnitude difference between the edges and the middle side. You cannot see this because it's normalized, but in reality, when you calculate it, the charge will be very different in the middle compared with the source and the drain. And the machine learning was struggling a lot because it could not, this huge difference in the charges, the magnitude of the charges and everything else, the parameters that they're coming, was really creating problems. So from your point of view, when you do this, what we said, okay, we'll create so-called positional mapping. You can have this, let's say it's in the source, it's 0, 0, and it's one of the layers that goes, or one of the descriptors that go in the machine learning. And when you're on the other side, when you're in the drain on this side, you have 1. This is arbitrary number between 0 and 1. Can be function, we did it with the cosine, we did it with any other function. So when you do your machine learning, maybe it's good at some system, and this kind of gives you transferability as well, because if you increase or decrease the size, you might be able just to change the positional encoding of the system, and you don't need to touch the black box that we really don't like. We might be able just to touch the positional encoding along X and along Y, and we may be able to make this much more transferable just with one layer of complexity that we can work with. It's an open question. We can still explore and see if it works. So, but in this specific case, we calculated the Green's function output, and this is the, let me try to stay. So this on this side is the machine learning, and this is the Green's function, like the target. So this is the target, this is the machine learning. They were quite nice matching on top of it. I think the error was less than 3% or something similar. We can make it better. But if you go further, basically this is the main outcome. So if you go and measure this device here in this clean room on this side, well, most of the time the people will give you IV curve, which is this curve on this side, current versus voltage, and will give you capacitance maybe. So the real output characteristics usually is this IV curve here. And I think the blue and the green are the target, the orange and the red are the machine learning tool that we did. And the main point is that if you kind of go through higher voltages, this is the machine learning part, and this is the normal part. And you can have kind of all of this stays around 6 iterations. Some of this gets go up to 12 or 14 or something similar. So in this kind of black box approach, taking out of it like the system just literally from the internet and adding just one layer positional encoding to the system, in principle, you can be able to speed up to 60%. When we submitted the paper, they really insisted what machine we used and how we used and how fast how it went. So it went for, let's say, 400 minutes to 200 minutes on this specific workstation and so on and so on. And it's more or less geometrically agnostic. If you make it bigger or smaller, at least you get the rectangular should behave in the same way, maybe just tuning a bit this positional encoding matrix. This is the the bottom message. So we can think about this later if this is useful or not, and how the things are done. Okay, we can have some chat later about this. The other thing that I wanted to show is biosensors. We never talked about this so far, and I think it will be something that might kind of give you some ideas. So biosensors, I have a project with some people from Luxembourg that we want to make, do you know lateral flow test, right? The COVID time when it was lateral flow test is paper more or less based. You have some liquid, put it on, and this comes with the lines and so on and so on. It's kind of good, but it's not very accurate. It's maybe 50-50 because it gives a lot of false positive, which is not really good. The standard when you wanted to be sure that you have to know if you have COVID or not was PCR. You remember this? You go and they'll send it to the lab and you come 3 days later. And if you need to fly, you need to write 3 days later. So PCR, how it works is it's kind of based on mass spectroscopy. One of the things what you do, you take the protein, the big molecule, you chop it on different pieces. And when you chop it, so imagine Lego block, so you have a star. I don't know, what is your favorite Lego piece? Tell me some, I don't know. The Death Star, do you know Star Wars?
Yes.
Okay, the Death Star. Is there Lego Death Star or not?
Pretty sure it is.
Yes, okay, so take the Death Star, you dismantle in the specific pieces, not on the small one. And what you can do, you can weight these pieces and you weight, let's say if it's dismantled on 15, you can weight these pieces and you can say, oh, okay, I know the weight of each individual pieces. I'm measured against database. So this assumes that the Death Star is decomposed. So it's a Death Star, it's a protein. So this is also time consuming, very expensive. What you can do better. You can use nanotechnology. Actually, this is what we have. So the transistors to measure one of these molecules or some of the molecules on the surface and use the charge. We can talk about this later. But if you do this, there is a huge potential these things to become much faster and cheaper because this is very cheap. So instead to have lateral flow test in piece of paper, you literally can put it here on your phone. You can put your saliva, and this in principle should be able to measure what it is inside if you for specific markers and so on. So this is where it goes, the whole story. So how we combine this with the machine learning? So just to give you quickly again, so this is a source and a drain. So this is a transistor, this is a gate oxide, and this is some molecules on the top. And you want to know what are the molecules on the top. Is it a COVID virus or is something else, right? So this what is the question. So what you want to see, you want to kind of measure the response of this system, and you can do it numerically, analytically. We did it analytically because it's faster, and kind of my industrial collaborator or experimental guys said, I don't want to install any code. I don't want to work MATLAB. I don't want to learn Python. I want to have Excel sheet that if I press the button, this comes out with something. Okay. So when you do some stuff, also this you need to kind of take into account for who you make it and what it is. So some experimental people really don't have the money, the time, and the resources to have these fancy numerical simulations or whatever license that you want to do. So my collaborator said, I'm okay with analytical stuff. I want analytical equations. As far as you give me a rule of thumb, it's fine. So this is what we did. So I'm not going to go in details, but these are the calculations that you can use. So again, as you can see, you have equations that gives you some output. In this case, gives you a potential on the surface. Sorry, if I find this, so it gives you potential here on this surface, and you can, this potential is going to perturb the current that goes from the source to the drain, and you can measure what's on the top, basically how much current is perturbed when you go from the left to right. So this is the main idea. The main thing, just to open bracket, so the way how you measure things, usually, so if I want to, what I do now, and you do the same, you look at me and I look at you the way I scattered, and you measure the distance between me and you basically optically, right? So your brain calculates the light, this basically optical signal that comes. The other way to measure something is to weight it, right? So if I have the weight of all of us in a database and I just measure the weight of one chair, and if it's, let's say, 100 kilograms, all this most probably is Vihar. Right? Okay. I'm not 100, but for that. So the other thing you can measure, so you optically detect something, you weight something, this is what the mass spec does. And the third thing what you do here is you have a charge, which is on the top of this table, and it's like the magnets. If this is positive and the electrons are negative, they go here. If you put the charge, this will repulse the electrons here, and you have repulsion, and you change the potential. So you can measure all of us if we have different charges as well, in principle. So this is the idea here. So the potential is here on the top, and this how perturbs the current if I measure on left to right. And I'm going to kind of go quite quickly. This amino acid. So the keyword for here is large language models. So what we did, we took something that is really good in reading letters. Okay, we took large language model. It has been traced for billions and gazillions data. We don't have enough data for these transistors because there is not enough data for this. So the question is, can we take something that is trained? We know that is trained well. It performs well. It's a black box, but it has a lot of scope to kind of explore different things and apply it. And the way when we started looking at this is, if you look, this chemical here is called glutamic acid, and it has a letter E. This guy is called lysine, has letter K. All the amino acids on the planet, there are 23, 24 amino acids, has letters. So if you look at it, you can make sentences. Okay, so your DNA can be explained with letters, K, A, B, C, B, D, D, and you can have billions of letter sequences. Okay, so I don't care what is the chemical composition. I don't care at the moment how this thing looks like chemically. What I really want to see is that, can I make a correlation between this letter and the signature, which comes when I measure. So if you look here, this is a pH. pH is tells you how the environment is different. So in this cup, I have water. The pH is around 7, neutral. If I put juice, it's more acidic, so it's around 4 or 5. And if I put base, it's on this side, it's more. So this pH also is important, but we'll talk about this later if you want. By the way, the first person who used this and made a lot of money, it's a professor from Caltech in California, and he makes this. He did it in the lab. He did a spin-off, and he made a lot of money because in California they produce orange juice, and the company wanted to know what is the acidity of the orange juice, because if it's very acid, it's a lemon, and you don't want to drink it. If it's less acid, kind of here, maybe you want to drink it. So this was the first application of the technology that I'm showing you, to measure acidity of orange juice using this transistor electronic devices. And it came from anyway. So what you can see, the green guy, which is the K, has different response, and the orange guy, when I measure the potential. I'm not going to go in details why this is with called amino groups and so on. So I can distinguish between the green, between E and K. What also can distinguish is these molecules can be attached either on this way, so either can this stay or this way. So what I can distinguish depending on the charge, if they're standing like this and that, and this maybe becomes important later when you want to make a proteins. Okay, so again, letters that can be like in this way or that way. So again, you can distinguish between if it's sticking up with one side and sticking up with the other side. Again, and we were thinking what to do, how to make more fingerprints. So I'm going to call this kind of fingerprints that this molecule has, that I want to pass to the neural network in order to train it well. I can take a second derivative, and we took second derivative of this curve, because if you take a second derivative here, these points here are called point of zero charge, and actually they can be measured. So the guy in the lab actually can go and measure it, and he actually was after this more or less all the time, point of zero charge. And the other thing that you can measure quite easily is capacitance. So if you put something on the surface and you have different charges, you can measure capacitance. So these are the things that I can measure. I can feed it eventually from experiment to the machine learning, but there is not enough data. Okay, this is what Richard also said. We're struggling with the data. So can we make more data somehow? And this machine learning story is not going to work until we don't have a lot of data, and hopefully analytical model can help us to get this data. And just to give you a feeling what we do, so think about this a sentence. I don't know, sentence, DYKD. It's a letter, 4 letters together, has some output. If I measure the potential and the capacitance, so I have 2 fingerprints. If I do permutation, I change N and K, so I have a spelling mistake in the sentence. I'm going to get a different signal, and I'm going to have a slightly different signal. So now using, this is analytical, there's no machine learning yet, right? But in principle, if my analytical equation tells me the spelling mistake, I should be able to train a machine learning that should be able to, which is very good in sentences and letters, to tell me if it's there a spelling mistake or not, which in this case is called mutation. So if you have one amino acid change, usually this is the cancer. So you can have cancer, something happened wrong. And this is point of zero charge on one of this, point of zero charge the other this, we can measure this. And if we go further into the second derivative, you have some other things that you can measure. This is called point of zero charge, but this is called PK and PKB anyway, it doesn't matter. This is, you can measure. So you actually have more data. This you can measure. So this is known experimentally. You can maybe follow the curves and you can create more data. We can talk about this later. And this also can be measured on this side as well, here on this side. So in the end of the day, what we did, I guess you're getting the idea where they're going. So we have some experimental data that we can validate. We have some kind of curves that we measure, can be Ivy curves, can be Santos curves that I don't know, the skirmion is traveling in this way, but actually it's making some things like this. Can be principal metal CK diagram, whatever, different curves. If what we're just trying to do is trying to have additional fingerprints extracted from this data to help us to train the machine learning. This is what we're trying to do. And if we go further, what we did, this is the analytical simulations. We discretize this basically in different, the same axis, but different in different spatial distribution. We just made a vector from 1, 0 to 1, what you always do in order to pass it to the machine learning. And we chose this kind of points here that they're experimental, we call it tokens. So now you know where we're going. So we're going to generate tokens for this machine learning neural network that is extremely good in language to hopefully to be tried to predict what's going on there. So you have tokens for a potential, token for a capacitance. You run the large language model machine learning that you just took from internet. You kind of think that you trust, and you can predict what is happening. So the bigger picture is, at the end of the day, when we have this machine learning trained, we have only few measurements that is going to be passed to this, and hopefully it's going to tell us if there is a spelling mistake or not in our sentence that we're looking for, because we will know what we're looking for. And if you go further, this is the analytical and this is the machine learning output, they match more or less. I'll open a huge bracket here. They don't always match. And now what we're doing with me, my other PhD student when it comes, you can put something which I call it synthetic data or artificial fingerprints or something like this. So now what we're looking actually on the area of these molecules. So the molecules at the moment I said that I don't care about the chemistry. I just care that this is E and this is K. Doesn't always work. Actually, if you take the chemistry, which in the moment we're taking as an area, I can simply say that K is slightly smaller in area compared to E. If I have spelling mistakes and permutations, it works a bit better. And there are other things that I can go further and explain, but this is the main idea. So I'll finish here, and I'm just going to try to summarize. So we have equations, analytical, that produce curves. This is what you have. These curves might have a hidden data information, which may be second derivative, first derivative, area under the curve, slopes, or anything else. You can extract this and maybe use it to the machine learning to give it more information. Also, you might be able to cross-validate with some experiments, even if not enough experiments data, you might be able to do this. And still, you can use the black box approach to try to make some progress and estimate some stuff. Okay, I'll finish here. So thank you very much, and we can discuss more about that. Stop recording.
Time to record reversal.
Yes.